we've looked at this function previously. We look at the function f of xy equals xy, and we ask ourselves, where's this function going to be have the greatest value? Where's it going to have the least value? What's its behavior going to be like? Okay, well, we can look at this function as we kind of did before along the line y equals cx. Now that's actually a plane in three-dimensional space, the plane y equals cx. But if we confine ourselves down in the x, y plane, y equals cx is going to be a line through the origin with slope c. We could have a slope of 0, which would be a line along the x-axis corresponding to c equals 0. We could have c equal 1, which would correspond to a line of slope 1, a line halfway between the x and the y-axis. Here we have a c value somewhat less than 1. Maybe that's 1/2. Maybe this is c equals 2. And here maybe c equals -2, c equals -1/2. So just orient ourselves to the idea of confining ourselves to a plane. Again, we looked at that in the context of taking limits. So it's not an unfamiliar idea. Then our function f of xy, which is equal to xy, becomes, replacing y with cx, f of x cx equals cx squared. So that in an xz plane, and the plane y equals cx can be written as an xz plane, we have the parabola for maybe c greater than 0. Well, if c is greater than 0, we're going to get a parabola that looks like this. Okay, our z equals cx squared parabola will open upward. And there's a critical point then in the y equals cx plane, and that critical point would lead us to the conclusion that the function has a minimum at this point. However, if c is less than 0, as it is over here on the blue lines, then z equals cx squared is going to be a parabola opening downward. It's going to look like this, and we're going to conclude that our critical point gives us a maximum. Now that's true in this plane. Okay, if this is one of these planes or any plane where we have that corresponds to a negative slope, we're going to conclude that we have a critical point at the origin, and that critical point gives us a maximum. Within that plane, that's true. If we're in any of these planes where the slope is positive, the slope of y versus x is positive, we're going to have a parabola opening upward, and we're going to conclude that our critical point gives us a minimum at the origin. Now, when we look at the function as a whole, above the xy plane, we would have the z plane coming out of the axis, or coming out of the board. Okay, on the purple lines, we would have parabolas opening upward. And that would be the intersection of the graph of this function with this plane. The intersection of the graph with this plane, the parabola would again open upward. It would be even steeper because the value of c, the slope, is even greater. So the parabola is narrower, steeper, however you want to look at it. As we cross the y-axis, though, the slopes all of a sudden reverse and become negative, and the parabola start opening downward. So if we want to look at what happens as we approach the origin, the value of the function does approach 0, but it's not like a paraboloid where we have a definite minimum, because our parabolas open upward in the first and third quadrant and downward in the second and fourth quadrants. And if you think about what that looks like, it's actually a hyperboloid, where it's opening upward this way, opening downward in this perpendicular direction. And you have what's called a saddle point. Now you can look at the pictures in your book. I'm not going to attempt to draw a good picture of a saddle point, but you can look at what that, you can look at the pictures of saddle points and relate that to what you're seeing here. In this saddle, and this is not a very good saddle because it keeps getting steeper as you go this way. It's kind of lopsided, but if you're facing in this direction, the saddle holds you in. You're cupped within the saddle, and then it opens this way in these directions so your legs can go over the side. Okay, well, this is an example of a function for which, if you look at it in certain directions, appears to open upward, but if you look at it in other directions, it opens downward. It gives you the saddle point in the three-dimensional graph is going to be then a saddle point.